Welcome to these NPTEL lectures on dynamics and control of mechanical systems. This week we are looking at classical control approaches. My name is Ashitava Ghoshal. I am a professor in the Department of Mechanical Engineering, Center for Product Design and Manufacturing, and also in the Robert Bosch Center for Cyber Physical Systems, Indian Institute of Science, Bangalore. In the last lecture, I had showed you that in order to find the effect of the external disturbance on the output or the effect of the internal parameter changes on the output using the state space representation, we had to perform a convolution. Okay, it was not very easy to quantify what would happen to the output if the internal parameter changes by some amount. Whereas if you looked at the same system using Laplace transforms, it was very easy to quantify the effect of the internal parameter changes or the external disturbance on the output. I had also mentioned that if you want to look at more complicated systems, basically systems which are not as simple as a single motor driving a link, but if you had a differential equation which was higher order, then we had to look at what is called as a root locus. In this lecture, we will study root locus in more detail. Root locus is one of the most well-known classical controlled system analysis and design technique. It was developed by Evans in 1948. So it's a reasonably well-known, mature and established technique for control system analysis and design. In the root locus approach, we start from the ordinary differential equation which describes the system. So we are dealing here with linear ordinary differential equations. Once we have the ordinary differential equation describe the system, we use Laplace transforms to obtain the transfer functions. So this is also sometimes called as a S-domain technique. So basically the transfer function is the ratio of the output to the input in the S-domain. So the ratio of the output to the input can be written in terms of two polynomials. So we can have a numerator polynomial and a denominator polynomial. The roots of the numerator polynomial are called the zeros of the transfer function, and the roots of the denominator are called the poles of the transfer function. And root locus is basically how the roots of the denominator of the closed loop transfer function change with the gain in the S-plane. So the transfer function will have some gain, some constant term k into a numerator polynomial divided by a denominator polynomial. So this is the open loop transfer function. The closed loop transfer function can be also obtained in terms of the open loop transfer function. Okay, and then we look at how the roots of this denominator polynomial of the closed loop transfer function change as the gain k is changed. So this is the basic approach of a root locus. We can obtain the time domain information from the inverse Laplace transform whenever we want. The disadvantage of the root locus or the limitation of the root locus is that it is limited to single input, single output system. So let us take the example of the single link driven by a DC servo motor. We have looked at this example many times in the past. Let us continue with that example. So for this example, the plant or the dynamical system can be given by this transfer function k divided by s into js plus f. The input to the dynamical system is the voltage, and the output is the rotation of the motor shaft, which is denoted by theta of s. This is the open loop transfer function of this link driven by a DC servo motor. open loop because there is no feedback. This is a second order ordinary differential equation in terms of the rotation theta of t, and the second order ordinary differential equation is given by j into theta double dot plus f into theta dot equals k into Va of t. So this is readily seen from this S domain. So here we can see that theta s divided by Va of s is k divided by s into js plus f, and the ordinary differential equation from this output by input is given by j theta double dot plus f theta dot equals k into Va of t. Okay, so Va is the voltage which is applied. For zero initial conditions, this ordinary differential equation, we can obtain the Laplace transform, and this is given by js square plus fs whole bracket into theta s, that is equal to k into Va of s. Okay, and this is basically what is shown here in this block diagram. So the transfer function between theta s and Vas is theta s divided by Vas is k divided by s into js plus f, which is exactly what is shown here. The roots of the denominator, which is s into js plus f, are 2. Okay, so it's a quadratic equation. So we have one root which is s equals 0 and the other root which is s equals minus f by j. To repeat, the transfer function between the rotation of the motor shaft, which is theta s, and the applied voltage, which is Vas, is given by theta s divided by Va of s is equal to k divided by s into js plus f. So recall, j was something to do with the inertia of the system, f is the friction, and k has to do with the kt and kg and Ra, the properties of the motor. We can plot these poles and zeros. So poles are the roots of the denominator polynomial. In this case, it's a quadratic polynomial. It is s into js plus f equal to 0. That is how we will find the roots of the denominator polynomial. So there will be two such roots, and we will plot these roots in the s-plane. So the s-plane consists of a horizontal axis, which is the real axis denoted by rs, and a vertical axis, which is the imaginary axis. So the f and j are positive in this expression, in this transfer function. So hence the two roots of the denominator are s equals 0, which is at the origin of the s-plane, and s equals minus f by j, which is in the left half of the s-plane. Why left half? Because j and f are positive, so s equals some minus some number. This is shown in this figure. So the vertical axis is the imaginary axis in the s-plane. The horizontal axis is the real axis. So one root is at 0, 0, and the other root is at minus f by j on the real axis to the left of this imaginary axis. So these two roots, s equals 0 and s equals minus f by j, are called the open loop poles, because this is the open loop transfer function. We have not yet considered feedback, or we haven't yet considered closing the loop using feedback. We must have two open loop poles. If you go back and look at the original second order differential equation, so if you have a second order differential equation, you will have two poles. Okay, when you convert that ordinary differential equation using Laplace transform, you will get a quadratic function, and the quadratic function will always have two roots, and they are the two open loop poles. So to obtain the response of this system, which is theta s divided by Va of s equals k divided by S into Js plus F, we need to give an input which is VA of S. So there are various possible inputs which we can give. In control system analysis, one of the standard input is a step input. A step input is given in this form. So VA of S is 1 over S. So a step input means for t less than or equal to 0 it is 0, and t greater than 0 it is 1. And the Laplace transform of such a function in time domain is 1 over S. So once you substitute VA of S as 1 over S on this side, we can see that theta of S is k divided by S into Js plus F into 1 over S. We can use partial fractions of the right hand side and we will get three terms. There will be one term which will be a constant, then there will be another term which will be something divided by S, and then there will be a term which is coming from k divided by Js plus F. Okay, so the constant term is basically something like 1 over S. The term which is coming from 1 over S square is b into t, and the term which is coming from 1 over Js plus F will be c e to the power minus f by j into t. Okay, so we will have three terms. I am not showing you what are these three terms, a, b and c. They are the numerators of the partial fractions. And once you take the inverse Laplace transform, you will get the theta as in time domain, which is given by some constant, plus b into t plus c into e to the power minus f by j into t. So we can plot now theta of t as a function of time, and you can see that this amplitude theta of t will increase with time. So it looks like this. So initially there is a small exponential portion. After that this linear term dominates, and we can see that it is increasing linearly with time. In all these examples, I have used k equals j equals f equals 1. We could have some other numbers for k, j and f, but just to show what will be the output of such a system. And what was the system? It was a simple DC motor rotating a link of a robot maybe. So we can find the output, which is rotation of the motor shaft, when you apply a voltage in time. And in this case, the voltage that we are applying is a step input. So now let us consider the single link being rotated by a DC motor, and we now consider a closed loop or the system with feedback. So the block diagram now looks like this. So we have the dynamical system, which is the motor plus the link which is being rotated by the motor. There is an applied voltage, and the transfer function of this dynamical system is k divided by S into Js plus F. The output is the rotation of the motor shaft, which we measure and then we feed it back. There is a desired theta which we want the link to rotate by as a function of time. So we obtain the error between theta d of S and theta of S. So this is the error, and then we multiply the error with this Kp, which is the controller transfer function, and the output is the voltage. So VA of S is Kp into theta ds minus theta of S. In this example, we will also assume that there is no external disturbance. So the theta d of S is the desired, or sometimes it is also called as the reference, and theta S is the output. The controller transfer function, as I have mentioned, is a constant. This is the simplest possible controller, and the constant is denoted by Kp. The closed loop transfer function between theta S and theta d of S can be obtained as theta S equal to k divided by S into Js plus F into Vs. So theta S is this into VAS, because the input to the block is, or this transfer function is VA. So theta divided by V is the transfer function, or theta is this transfer function into voltage. And then we can substitute voltage is nothing but Kp into theta d minus theta. So we will have K divided by S into Js plus F into Kp into theta d minus theta. So what you can see is we have on the left hand side one theta, and on the right hand side we have another theta. So we can simplify these two expressions, and after simplification we will get theta S divided by theta d of S is K Kp divided by S into Js plus F plus K into Kp. This is a very standard form of a transfer function in a feedback system. So if the open loop transfer function is K divided by S into Js plus F, and we have a controller and we have a feedback, then the closed loop transfer function will be K into Kp. So this is like gains K into Kp divided by S into Js plus F plus K into Kp. This can be further simplified or written in a slightly nicer form, which is K Kp divided by J. So we want the coefficient of the S squared term to be 1. So we can divide the denominator by J and numerator also by J, and we can rewrite the transfer function theta S by theta d of S as K Kp into J divided by J, and the whole thing divided by S square plus F by J into S plus K Kp divided by J. The two roots of the denominator polynomial are given by this. So it's a quadratic equation. It is of the form x square plus bx plus c. So we can rewrite the expression for the two roots is minus into f by 2j plus minus 1 by 2 into square root of f by j whole square minus 4 k kp divided by j. So this is nothing but the solution to a quadratic equation which we know in closed form. Okay. The two roots of the denominator, which are these two s1 comma 2, these are also called the closed loop poles, because now we have feedback, we have the transfer function between the output and the input theta d of s, and the roots of the denominator polynomial are called the closed loop poles. So this can be shown in this S plane. So now we have again the real axis, which is R of S, and the imaginary axis, which is I of S, and we have the open loop poles, which are 0, 0 and minus F by J. Now if I change Kp, then we can see that the roots will change. Okay, so the expression for the closed loop poles are minus f by 2j plus minus half into this thing under the square root, which is f by j whole square minus 4k kp by j. So I can increase kp. So when I increase kp, you can see that after a while the term under the square root will become 0, and then this term will become larger than this term, and we will have imaginary roots. So this is what is shown here. So it starts from minus f by j and 0. As I increase kp, these roots, one root will go this way, the other root will increase, and then after a while it becomes imaginary. And when kp tends to infinity, okay, then these branches will go, one will go up and one will go down. So for kp equal to 0, you can see that S1, 2 are the open loop poles. So if I substitute kp equals 0 here, then you will get one root which is at 0 and one root which is at minus f by j. And as you increase kp, the two roots will approach each other in two branches, and at kp equals f square divided by 4j into k, the two branches will meet. So the term under the square root will become 0 and they will meet at s equals minus f by 2j. And if you keep on increasing kp after that, this term will become negative and the square root of the negative number is imaginary, and hence the two branches will, one will go up and one will go down, and both go to infinity. So this is called as the root locus of the second order system. So we had a second order system because we had a differential equation which was j into theta double dot plus f into theta dot is equal to k into VA, and then we had this feedback, and then we had this two poles or the two roots of the denominator polynomial. These roots depends on kp, and as you change or as you increase kp, the location of the roots change in the S-plane. So this is how the roots change in the S-plane is called the root locus. And this example is the root locus of a simple second order system. So let us continue with the second order system. So as I said, the root locus of the second order system, which is the ratio between the output theta of s and the input theta d of s, can also be written in this form, which is theta s divided by theta d of s is omega n square divided by s square plus 2 psi omega ns plus omega n square. This is a very, very standard form for writing the transfer function of a second order system. In this form, this omega n is also sometimes called as the natural frequency, and this psi is called the damping. In our case, the natural frequency omega n square is given by k kp divided by j, and the damping is related or can be obtained from this expression, which is f by j is 2 psi omega n, and hence psi is f divided by 2 into square root of j into k into kp. So this idea of natural frequency and damping has been borrowed from mechanical vibration. So when you have a spring mass damper system, we can find what is the natural frequency of the spring and mass related to the mass and spring, and the damper is from the damping term in the vibration equation. So in second order systems, we have borrowed those terms, and this is the standard way of looking at a second order system in terms of a natural frequency and damping. So in a second order system, these are the two characteristic parameters. One is the natural frequency and one is the damping. So this transfer function is again second order simply because the governing ODE was of second order. Okay, we derived the equation of motion of this link rotated by a DC motor, and it was a second order ODE. So hence it is a transfer function is called second order. Another way of looking at or calling it second order is that the denominator polynomial is of degree 2 in S. Okay, so if it is a second order system, the denominator polynomial will be of degree 2 in S. And as I said, for all second order systems, there are two characteristic parameters. One is omega n, which is called as the natural frequency of the system, and one which is psi, which is called the damping. So the parameters omega n and psi completely determine the behavior of a second order system, because these are the only two parameters. And what the values of omega n and psi, they completely determine the behavior and the nature of the second order system. So there are three possible kinds of behaviors or three possible nature of a second order system. One is when psi lies between 0 and 1. This is called as an underdamped system. When psi is equal to 1, this is called as a critically damped system. So when the damping parameter is between 0 and 1, this is underdamped. When the damping parameter is 1, it is critically damped. and when the damping parameter psi is greater than 1, it is called as an overdamped system. Again, those of you who have done any course in vibration, these terms might be familiar to you. So there are three possible natures of a spring mass damper system. One, when it is underdamped, when psi is between 0 and 1, and one which is critically damped, and one which is overdamped. So let us continue with the second order system. We are looking at the case when 0 less than psi less than 1. So this is the case of the underdamped system where the damping coefficient lies between 0 and 1. So there are lots of figures and lots of material in this slide. So let us go over slowly. So what I have on the left hand side of this slide is, this is the S plane. So this is the real axis, this is the imaginary axis. So the open loop poles are at 0 and minus f by j. So we are still looking at the single link rotated by a DC motor, and we had derived the equations of motion, and then we had derived the transfer function, and we had written it in terms of the natural frequency and damping. So when psi is between 0 and 1, the transfer function can be written as theta s divided by theta d of s. So theta d is the desired or the reference input, can be written as omega n square divided by two products, okay, two linear terms. So one of them is s plus psi omega n plus j omega d. The other one is s plus psi omega n minus j omega d. So let us quickly see what is this omega d and omega n. So consider some value of Kp for which the poles are at these two crosses. So these are two complex conjugate poles, and the real part of this pole is minus f by 2j, and the complex part is from here. Okay, so this is square root of f by 2j whole square minus kkp by j, but kkp by j is greater than f by 2j whole square. So this is one complex pole and the other one is the complex conjugate pole. So in this figure, what you can see is there is an angle theta. So if I look at this pole, then if I see this angle theta, sine of theta will be the damping. So theta is sine inverse psi. The distance of this pole from the origin is the natural frequency omega n. So these are again very standard things which we can derive from the concepts of vibration, or we can even derive from the equations which I have discussed earlier. So if you take some effort, you can show that the distance is omega n and this is sine theta is psi. We can also find out what is the expression of theta as a function of time. The expression as a theta as a function of time is 1 minus e to the power sine omega nt into cos omega dt plus psi divided by 1 minus sine square sine omega dt. So what is omega d? Omega d is the distance of this pole for a given Kp from the real line. This distance is psi into omega n. So because if this angle is theta given by sine inverse psi and this is omega n, then this distance will be psi omega n. So what is omega d? Omega d is omega n into square root of 1 minus psi square. So you can see this. So this is omega n, this is psi omega n. So this omega d is given by this expression. So the theta d as a function of time can be written in terms of psi omega n and of course omega d, which is in turn derived from omega n and psi. So as I mentioned earlier, everything about the second order system can be written or described in terms of psi and omega n. So the right hand side of this slide shows what is the behavior of theta t, or what is the plot of theta t for a given step input. So again, what is the step input? It is this dark line. So theta of d of s is 1 over s. So that is the step input. So we want to find out what is the theta of t for theta d of s as 1 by s. So what do? We write theta of s is equal to this omega n square divided by this into 1 over s, and again we do partial fractions, and then we find out the various terms when you do inverse Laplace transform. So it turns out that we will get theta of t as 1, some constant term, then there will be some e to the power minus psi omega n t into cos omega dt plus psi divided by square root of 1 minus psi square sine omega dt. Again, those of you who have done any course in vibration or even some ordinary differential equation course in your undergraduate, you can see that we can get the solution to the second order differential equation when psi lies between 0 and 1 is of this form. Okay, so let us plot this theta of t. So this red curve here shows the plot of theta of t as a function of time. So one of the first thing that you can see is that this plot of theta of t always lies between these two asymptotes. And what are these asymptotes? It is one is 1 minus e to the power minus psi omega n t divided by square root of 1 minus psi square, and the other one is 1 plus e to the power minus psi omega n t divided by 1 minus psi square. So when you give a step input, the theta will cross the step input and then keep on oscillating until it comes within a certain band. So the maximum height which it exceeds this 1 is called MP. This is called as the peak overshoot, okay, in a second order system. This happens at a time Tp. Okay, we can also define 3 other times. One is something called Td, which is the delay time, and that is basically when theta of t reaches half of 1, half of the input. Input is 1 here. So this happens at Td. Then we also have something called as the rise time. There are various ways of defining a rise time. In this picture, I have shown the rise time when it goes from 0 to 100% or 0 to 1. The time required for theta of t to reach 1 the first time. So this is Tr. And then there is one more very important time which is called settling time. So basically this is an oscillatory response. The theta of t will overshoot and then keep on dying down. And once it reaches within an allowable band, and there are 2 kinds of allowable bands which are in use. One is 5% of this 1 of the input or 2% of the input. So this is either plus minus 0.05 or plus minus 0.02. So the curve of theta t, once it enters this band first time, and it will not leave this band because it will keep on oscillating and slowly dying down, that is called as the settling time. So for a band of 0.02, you can show that this Ts is 4 divided by psi omega n. For a band of 0.05, it is approximately equal to 3 divided by psi omega n. The Tp, which is the time when it reaches this peak overshoot, can be shown to be pi divided by omega d. Omega d, remember, is again the damped natural frequency. It is called the damped natural frequency because it is omega n into square root of 1 minus psi square. So Tp is pi divided by omega d. The value of Mp can be also obtained by substituting when the derivative of this theta of t goes to 0. Remember, at the peak overshoot, this is derivative is 0. So we can find what is the value of the time when the derivative goes to 0, and also what is the value of theta of t at that point. Both of them can be found out. In fact, pi by omega d is obtained like that. And Mp can be obtained by substituting Tp in this expression for theta of t. and that is given by e to the power minus psi divided by square root of 1 minus psi square into pi. Okay, the rise time can also be obtained for 0 to 100% as pi minus beta divided by omega d, where beta is this angle. So it is theta plus beta will be 90 degrees. So beta is omega d divided by psi omega n. So sine inverse of omega d by omega n. Okay, so in this picture I have shown you all the things that are important in a second order system. So what are some, just let's recap. So in a second order system, as you change Kp, which is the controller gain, the root locus behaves in this manner. So it starts from this open loop pole when Kp equal to 0, one pole is at 0, one pole is at minus f by j. As you increase Kp, the branches of the root locus, there are two branches because there are two poles and it's a second order system. So there will always be two roots. So they come towards each other. They will meet at a point when the roots will become equal. And after that, if you keep on increasing Kp, the roots will become imaginary. Once it is imaginary, let us pick a point here and I can prove to you that the distance of this point from the origin is not the natural frequency. And the angle which this line makes with the vertical imaginary axis, theta, is sine inverse psi. Okay, so for a step input to this second order system, the output theta of t will behave in this manner, which is given by this equation, which is 1 minus e to the power minus psi omega nt, then some cos omega dt plus something into sine omega dt. Basically, it lies between two asymptotes, which are 1 minus e to the power minus psi omega nt divided by 1 minus psi square and 1 plus the same thing. And based on this nature of this oscillatory input, which is dying down when I give a step input, we can define something called as the peak overshoot. Then we can define something called as Td, which is the delay time. Then we have something which is like the rise time, and then peak overshoot time, and then settling time. So in any second order system, as we will see later, this MP and TS is very important. Okay, so sometimes the specification for a second order system, the controller specification, will be such that we want such and such MP and such settling time. So if you give some numbers for MP and settling time, we can sort of infer what should be the damping and the natural frequency. We can also then go back to this picture and see where the poles of the desired closed loop system should be. Of course, this is only for a second order system. So in summary, for an underdamped system, when psi lies between 0 and 1, when the damping coefficient lies between 0 and 1, the output oscillates about the desired input, which is 1, before settling down in infinite time. Okay, it is important to realize that it will keep on oscillating, and only when t tends to infinity it will become 1, because this is like e to the power minus something into t. The settling time Ts is the time taken for the output to reach within plus minus 5% or plus minus 2% of the input. So for plus minus 5%, the settling time is given by approximately 3 divided by psi omega n, and is approximately 4 divided by psi omega n for 2%. So if you want a narrower band, you have to wait longer. So this is the time which you have to wait such that the output reaches within a band, which is either plus minus 5% or 2%. The maximum overshoot is large for low damping. Okay, you can see that the peak overshoot formula is given by e to the power minus psi divided by square root of 1 minus psi square into pi. So if you have low psi, okay, then we'll have larger peak overshoot. The roots of the denominator of the closed loop polynomials are complex with negative real parts. Okay, so it is on the left half plane and it is going towards infinity. The roots are in the left half plane, so hence the second order system is stable. Remember, according to Lyapunov, the roots of the polynomial, if they are in the left half plane, they are stable. If they are in the right half plane, they are unstable. In this case, for the second order system with damping between 0 and 1, the roots are always on the left half plane and hence the system is stable. Let us continue with the second order system. Now we will see when you have critical damping. So basically psi is equal to 1. So these are called critically damped systems, and in this case we can again plot the output theta of t, okay, as when you give an input or step input of 1. So theta d of t is 1 for t greater than 0 and it is 0 for t less than or equal to 0. So we can again find the solution from inverse Laplace transform of the second order system, and it is given by theta of t as 1 minus e to the power psi omega nt into 1 plus omega nt. Okay. There are two possibilities. One is if the initial theta dot is 0, then it will always lie below this line, below this theta d equals 1. If theta dot 0 is not 0, okay, but if it is, let's say, greater than 0, then it can overshoot this theta d equals 1, but it will overshoot it only once. So in both cases, as you can see, as t tends to infinity, theta of t will approach 1. So the transfer function for critically damped system is omega n square divided by s plus omega n square. So this is a repeated root. The denominator has repeated roots. The output for a step input, which is theta d 1 over s, is given by 1 minus e to the power minus psi omega n t plus 1 plus omega n into t. Okay, this is again using partial fractions and inverse Laplace transform. So we can work it out and you will get this theta of t. The output for critically damped shows no oscillations and can cross the input at most once. The settling time can be defined similar to the underdamped case. Again, we can have some kind of a band here, plus minus 2% or 5%, and we can find the time such that it reaches this band. The roots of the denominator are real and repeated and lie on the left half plane. So again, since they lie on the left half plane, then again it is stable. Again, you can see also from the definition of bounded input, bounded output stability, if I give a bounded input of 1, the output is not going off to infinity. The output is also bounded. So this critically damped second order system is also always stable. Finally, we look at what is an overdamped system. So in the case of an overdamped system, basically we have two roots and both the roots are real. Okay, so we have omega n into psi plus minus psi square minus 1. So since psi is greater than 1, so the term under the square root will always be real. Okay, so we have two possible roots, and these two roots, so in this example I'm showing you one root as 1.5 and one root as 3.0 arbitrarily chosen. We'll have one exponential curve which is rising like this and the other exponential curve which is rising like this to meet 1. Okay, so if the damping is more, So psi is 3. So whereas this is psi is 1.5. If the damping is more, it takes longer to reach theta of t equals 1 or theta d equals 1. So again, the output for a unit step input, which is given by 1 over s, we can obtain by using inverse Laplace transform. So theta of t is given by 1 plus omega n square divided by 2 square root of psi square minus 1 into this e to the power minus s1t divided by s1 minus e to the power minus s2t divided by s2. Okay, whereas s1 and s2 are given by these two roots of the denominator polynomial with psi greater than 1. Again, the output theta of t can never cross the input and is the sum of two exponential functions. So you can see this is one exponential function, this is another exponential function. So the output is sum of these two exponential functions. The roots of the denominator polynomial are real and distinct and lie on the left half plane. Again, both the roots are always on the left half plane, and hence again by Lyapunov or by this notion of bounded input, bounded output, they are stable. So the second order system, whether it is underdamped, critically damped or overdamped, is always stable. Okay, so if you give a step input, the output will never go off to infinity. Let us continue and look at a numerical example. So in this numerical example, we have the plant, which is k divided by s into js plus f. We have a controller, which is proportional controller, very simple, simplest possible controller, a constant. The input is theta d of s, which will be a step input. We measure the output theta of s, and then we subtract, and this is the voltage which is coming into this plant. So this is the block diagram of the second order system, and we pick values of for psi equals 0.25 and kp equals 4. The output will look like this. So this is a much nicer and cleaner representation of what I had drawn by hand. Okay, and this is also obtained from MATLAB. So if you were to use MATLAB, you can show that the peak overshoot for this case, psi equals 0.25 and kp equals 4, and then again k, j and f is 1, you can show that the peak overshoot is 0.4432. So the distance from here to here is 0.4432. So it doesn't quite reach 1.5, but it is like 1.4432. The rise time is 0.36343 seconds. So the time to reach 1 is this. So this is not from 0 to 100. MATLAB allows you to choose whichever you want. So in this case, the choice made was from 10% to 90%, and the rise time is this. The settling time for 2% is 7.0579 seconds. So with MATLAB and with this function called step info system, okay, if you go back and look at MATLAB, which is available to all the candidates of this NPTEL course for free, you can simulate this system, second order system. We can substitute k, j and f equals 1, and then you can obtain what is the peak overshoot, what is the rise time, and what is the settling time. If you pick psi is equal to 1, okay, then the plot of theta of t looks like this. So as I said, this never crosses the theta d equals 1 line. And if you increase psi to 1.3, then it will be lower than this. So as the damping increases, it takes longer and longer to reach theta d of 1. Okay, and for each of these cases, we can find out what is kp. So kp is 1.4, and in this case, kp is 0.15. So MATLAB allows you to take this second order system, model it, and then give values of kp, k, j, and f, and then see what is the output theta as a function of time for a given theta d of s. In this case, theta d of s is a step input. So let us summarize this second order system. So a general second order system can be written in this form. G of s is some omega n square divided by s plus 1, s plus s1 into s plus s2. So this s1 and s2 could be real or they could be complex conjugate. So if they are complex conjugate, which means one pole is here and the other one is here, then the output of this system for an impulse, or if I just give it 1 as the input, theta d of s is 1, not 1 over s, then it will look like this. So it will oscillate and settle down at 0. If the roots are real and negative, so they are on the real axis, so let's say this is a -3 and this is -5, then you'll have two exponentially decaying curves. The one which is further to the left will decay faster because it is e to the power -5t will be much faster than e to the power, let's say, -2t. So this is a slower decay, this is a much faster decay. If the roots are on the right half plane, which means what? This is positive real part. Then if you take two complex conjugate roots and then if you give some input, the output will keep on increasing because it is like e to the power plus at. So if you give e to the power plus at will be an exponentially increasing plot. And since they are complex conjugate, they will also oscillate. If the roots are on the imaginary axis, so plus minus, let's say 3i or 3j, then they will keep on oscillating without ever dying down. If the roots are on the real line but on the positive or on the right half plane, then the output or theta of t will continuously increase. So if it is closer to the origin, it is increased a little bit slowly. If it is far away, it will increase much faster. In both of these cases, if it is on the right half plane, it will go off to infinity. And these are called unstable poles. So as long as the roots are on the right half plane, these are called unstable, whereas if it is on the left half plane, they are stable. This is unstable because it is going off to infinity. You can also think what happens if the root are at the origin. Okay, so what happens when the root are at the origin? Think about it. The answer is here. It doesn't change. So it will stay at the same value. Output will stay at the same value. So these are also sometimes called as the natural response for poles in the S-plane. So whether the poles are in the left-hand side, then it is dying down, either oscillatory or exponentially dying down. If they are in the right half plane, they are increasing. So either exponentially increasing if they are on the real axis, or oscillatory and increasing if they are complex conjugate. And if they are on the imaginary axis, then they neither die down nor increase. They just oscillate about the same place. What about higher order systems? So let us consider a general ODE which is given by y to the power n. Y to the power n means the nth derivative of y with time, plus a1 into y to the power n minus 1 plus dot dot an to the y, and this is equal to k1 into u to the power m plus b1 u to the power m minus 1. Again, u is the input and m means the mth derivative. Okay, so one important thing which we will see later, this m must be less than or equal to n, and we will see later why this must be true. So this is the general ODE, higher order ODE, containing nth derivative of y and mth derivative of the input u. We can take the Laplace transform of this equation with 0 initial condition, and we can obtain the transfer function between y and u. Okay, so the transfer function g of s, which is y of s divided by u of s, can be written as k1 into a numerator polynomial, which is s to the power m plus b1 s to the power m minus 1 all the way till bm, and the denominator polynomial, which is s to the power n plus a1 s to the power n minus 1 all the way to an. Okay, so let us assume that we can factorize these polynomials, or we can find the roots of these polynomials. Okay, and these polynomials can be written as k1 into s plus z1, s plus z2, and s plus zm. So this is the numerator polynomial, and the denominator polynomial can be written as s plus p1 into s plus p2 all the way till s plus pn. So since this is the nth degree polynomial, there will be n roots, and so these are p1, p2, and pn. They could be real or complex conjugate. We are not assuming anything right now. Similarly, the numerator is a mth degree polynomial, so it will have m roots, and these are s plus z1, s plus z2, and so on. So in root locus, these zi's, which there are m of them, are called the zeros of the open loop transfer function. Okay, so this g of s, which is output y of s divided by, say, the input to the plant, which is u of s, that is the open loop transfer function. So z1, z2 all the way till zm are the zeros of the open loop transfer function, and p1, p2 all the way till pn are called the poles of the open loop transfer function. So let us continue with the higher order system. Now we have a dynamical system which is given by k1 into g of s. G of s, remember, has a numerator polynomial with the zeros z1 through zm, and the denominator polynomial with poles, which is like s plus p1 plus into s plus p2 all the way till s plus pn. And the number of poles is n is greater than or equal to the number of zeros, which is m. So we have a controller, and we are going to consider the transfer function of a controller as a constant kp. The output of the controller is u of s. The output of the dynamical system is y of s, and we measure y of s with a sensor whose transfer function is 1, and then we have this reference input or r of s, and then the error is computed as r of s minus y of s. So e of s is r of s minus y of s. So the closed loop transfer function is y of s divided by r of s is equal to kp into k1 into g of s divided by 1 plus kp into k1 into g of s. Again, this can be derived. All we need to do is go step by step. We find y of s is k1 into g into u is kp into e is r minus y, and then you can simplify and you will get this closed loop transfer function. If h of s is not unity, basically if the sensor transfer function is not unity, we can take into account h of s inside g of s. So it is not a very serious issue, or without loss of generality, we can assume the sensor transfer function is unity. Next, we substitute k as kp into k1. So you can see that there are these terms kp into k1, both in numerator and denominator. We will substitute k as kp into k1. So hence, the closed loop poles are the solutions of the denominator, which is now 1 plus k into g of s equal to 0. So if we can solve the roots of this denominator polynomial given by 1 plus k into g of s equal to 0, then we can find the closed loop poles. G of s, remember, is given by k1 into s plus z1 into s plus z2 all the way till s plus zm divided by s plus p1 into s plus p2 all the way till s plus pn, where m is less than or equal to n. So we know the open loop poles and the zeros of the G of s. So we know what are the values of z1, z2 all the way till zm and p1, p2 all the way till pn. Okay, so we know the solutions of the numerator and denominator polynomials for G of s for this open loop transfer function. So question is, where are the closed loop poles? And that is basically the root locus technique. So we can use root locus to find the closed loop poles given the open loop poles and the zeros. So the root locus is basically the roots of the denominator polynomial 1 plus k into g of s equal to 0. Nowadays, with powerful computers and software such as MATLAB, we can very easily find them numerically. So remember, we are given the open loop transfer functions. So basically the zeros and poles of the open loop transfer function. All we need to do is form this closed loop denominator polynomial, which is 1 plus k into g of s, and we can very easily solve them numerically in MATLAB. And in fact, that is what everybody does. However, it is very useful to look at what was done before MATLAB was available. And the main reason why we want to take a look at how to solve or how to obtain the root locus by sketching is because it gives a lot of insight. MATLAB is a software tool. It will just give you numbers, but it does not really give you some of the insight which we can see if you try to sketch the root locus given G of s. So what is root locus? Let's summarize. We want to find values of s such that 1 plus k into g of s equal to 0 for 0 less than or equal to k less than infinity. Okay, as I increase or change this value k, which is, remember, kp into k1. So in some sense, as you increase the controller gain, what happens to the roots of the denominator polynomial? So let's see. 1 plus k into g of s can be written as k into s plus z1, z2, s plus zm plus p1, s plus p1 into s plus p2 all the way to s plus pn. So 1 plus k g equal to 0 is nothing but k into this term plus this term is equal to 0. And remember again, and we will come to this towards the end of this lecture, m is always less than or equal to n. So 1 plus k into g of s equal to 0 is a polynomial of degree n. Why? Because this part s plus p1 into s plus p2 and so on is a degree n polynomial, and we are adding to that a degree m polynomial. So the resultant polynomial is always degree n, and it must have n roots. Okay, so as k increases, all n roots will move on n branches. So if you have 2 roots, you will have 2 branches. And if you have n roots, you will have n branches. So as you change k, the roots will move on these n branches. So since 1 plus k into g of s equal to 0 is smooth and continuous, the branches cannot intersect. So think about it. If you have two branches and they intersect at some place for some value of s, then at that place you can have two different slopes. Okay, so the next solution can be in either of the two branches. So that is not allowed. Okay, because it is smooth and continuous. The condition that m is less than or equal to n ensures that it is a physical system, and we will discuss this again later. Okay, if m is not less than or equal to n, then it is no longer a physical system. Let's continue. 1 plus kg of s, as I said, can be written as k into s plus z1 into s plus z2 all the way till s plus zm plus s plus p1 into s plus p2 all the way till s plus pn equal to 0. So if you substitute k equal to 0 here, then the roots of 1 plus kg are nothing but the poles of the open loop transfer function. So the roots of 1 plus kg equal to 0 for k equal to 0 are p1 minus p2 all the way till pn. Okay, so these are the roots when k equal to 0. So we can conclude that the root locus starts from open loop poles of g of s. So p1, p2, p3, these are the open loop poles of the transfer function. So, and the root locus will start with k equals 0, and as k increases, the roots will travel on these n branches. So all the n possible branches, they all start from the given pi's, okay, from the n pi's. If k tends to infinity, the m roots of 1 plus k into g of s are minus zi. So you can see that if you divide this by k and then k tends to infinity, we are left with s plus z1, s plus z2 all the way till s plus zm equal to 0. So hence the roots are z1, z2 all the way till zm. So when k tends to infinity, m roots of this are the m zi's. Okay. So the m branches of the root locus end at minus zi, and what happens to the other n minus m branches? They go off to infinity because they cannot go anywhere else. So this is a very important insight of root locus. All the root locus starts from open loop poles, which is minus p1, p2 and so on, and then they end at the open loop zeros or at infinity. From 1 plus k g equal to 0, we can write g of s is equal to minus 1 by k. Okay, so now k is real and positive. So hence g of s must be real and negative. So k is some positive number. So minus 1 by k is a negative number. So g of s must be real and negative. G of s can be written in polar form. So what is the polar form? It is like if you have x and y, we can write x as some r theta. X comma y is in terms of r and theta. R is square root of x square plus y square. So that is the magnitude. And then angle is this angle of this vector from the origin to x comma y. So these are called the phase and the magnitude of g of s when it is written in the polar form. The phase of g of s must be opposite of k. So since g of s is equal to minus 1 by k. So this is a negative number, k is a positive number. So the phase of g of s must be opposite to that of k. So the phase of g of s at some arbitrary point s equals 0 will be equal to the angle made by the zi terms minus the angle made by the pi terms. Because what is g of s? G of s plus z1 into s plus z2 and so on divided by s plus p1 into s plus p2 and so on all the way till pn. So we can find the angle made by each one of these poles, which is the zi terms, which is in the numerator, and then minus the angle made by each of the other poles in the denominator with a minus sign. So the phase of g of s at s0 should be equal to this. Okay, so this is correct. So all points on the root locus must have a phase of gs of 180 degrees or 180 plus k into 360 degrees, k equals 0, 1, and that comes from this. So if I write g of s in the phase magnitude form, in the polar form, the phase of g of s must be opposite of k. So k is a constant. So hence all points on the root locus must satisfy this phase relationship, which is that the phase of g of s of 180 or 180 plus minus k into 360. So since there's a minus sign, it should be in the opposite. That is what 180 is coming from. So let us pick an example. So g of s is arbitrarily chosen as s plus 1 divided by s into s plus 2 whole square plus 4 into s plus 5. So what are the poles? There is a pole at 0. There is a pole at s at minus 5, which is here. And then there are these two imaginary poles. So you can see that s plus 2 whole square plus 4 equal to 0 will be minus 2 plus minus 2j. So there are these two poles, minus 2 plus 2j and minus 2 minus 2j. So let us pick a point, arbitrary point, and also there is a 0. So there is a 0 at s equals minus 1. Okay, so there are these zeros at z1 is minus 1, pole at s equals 0, s equals minus 5, and two imaginary ones at minus 2 plus minus 2i. So let us pick a point which is minus 1 plus 2i or 2j. Sometimes I am using I as square root of minus 1, sometimes it is j, which is square root of minus 1. Both are same basically. So what is the angle at this point? So we can see that the angle at this, due to this minus 1, is approximately 90 degrees. The angle due to this pole at 0 is 116 degrees. This is 76 degrees. This is 26.6. So what do we need to do? We need to see that the 0 is plus 90. This is minus 116. This is 0. This pole here will give you almost a 0 because it is on this ji2. Okay, and then this is minus 76 because this is at this angle. This is for a pole, it is in the denominator, and this for this pole it is minus 26.6. So if you sum up all these angles, we will get is minus 129.2. So this point is not on the root locus because it does not satisfy the condition that the sum of these angles should be equal to 180 degrees or k times 360 degrees. So pick any point in the S-plane, and for this transfer function we can compute the angles in this manner by drawing these lines and then looking at these angles. Okay, we can measure these angles very easily because remember it is r into e to the power I theta. So sine and cos theta we can obtain from these 2 points, and then we can add these angles, and if it is not 180 degrees then it is not on the root locus. The root locus is also present only on the real axis to the left of an odd number of real poles plus zeros. Okay, so if you think about it, so if the root locus can be only on the real axis and to the left of an odd number of real poles and zeros, Otherwise, this phase angle will not be equal to 180 degrees plus k into 360 degrees. Okay, so k could be 0, 1 and so on. So this is another very important rule in sketching the root locus. So we can easily see if on the real axis there is a portion of the root locus or not because of this rule. So as k tends to infinity, 1 plus k into g is 0 if g of s is equal to 0. So g of s is equal to 0 for the m zeros because g of s is numerator by denominator. So if the numerators are all s plus z1 into all the way till s plus zm, so the numerator is 0 for all the zeros. So the root locus will be near to m zeros of g of s. Okay, is that clear? Yes, because g of s will be 0, then 1 plus kg of s will be 0 when k tends to infinity. G of s also goes to 0 if s tends to infinity. So, and 1 plus kg of s equal to 0 can be approximated as 1 plus k into 1 divided by s minus alpha to the power n minus m. So remember, g of s is something like s plus z1 into s plus z2 to all the way till s plus zm divided by s plus p1 plus s plus into s plus p2 all the way till s plus pn. So the number of terms in the denominator is more than the number of terms in the numerator. So as k or s tends to infinity, 1 plus kg of s equal to 0 can be approximated like this. It is 1 plus k into 1 divided by s minus alpha into n minus m, because the m of them will sort of cancel out each other as s tends to infinity. So the root locus is asymptotic to the locus of 1 plus k into 1 divided by s minus alpha to the power n minus 1 equal to 0 for large k. Okay, so if you have a large k, then the root locus will be asymptotic to this. And all the asymptotic phase angles are equal to phi k, where n minus m into phi k is 180 plus k into 360 degrees. Okay, so remember the angle is 180 degrees plus k into 360 degrees, and for these asymptotes, when s tends to infinity, the phase angles are all given by this relationship. So as s tends to infinity, n minus m root locus are asymptotic to radial lines with angles phi k, and this angle phi k is given by 180 plus k into 360 divided by n minus m, and where k is 0, 1 all the way till n minus m minus 1. We are starting from 0, so it is n minus m minus 1. So this is another important insight, that as s tends to infinity, we can draw these radial lines, and then the root locus will be asymptotic to these radial lines. We can also find the center point of the root locus in the following manner. The denominator of this open loop transfer function is a n degree polynomial, s to the power n plus a to the power sn minus 1 and so on, because there are n poles. So the polynomials can be factored as s minus p1 and all the way to s minus pn. So the a1 or the coefficient of s to the power n minus 1 is minus p1 minus p2 all the way till minus pn. So minus ai is the sum of p1, p2, p3 all the way till pn. Is that correct? Yes. So you can see that if you have a quadratic which is s minus p1 into s minus p2, the coefficient of s will be minus the coefficient of s will be p1 plus p2. Likewise, for the numerator, we have s minus z1 and so on, and we get minus b1 is sum of the poles, sum of the zeros, zi. So for closed loop denominator polynomial, we have s to the power n. So this is the part containing the poles, and then k into part containing all the zeros. This is what we have. So as k tends to infinity, the sum of the roots of the closed loop polynomials, which is summation over I minus 1 to m, Ri, is equal to summation of I minus 1 to m, which is Pi. So hence, as k tends to infinity, m roots end in m zeros, and n minus m go to infinity from asymptotics 1 divided by s minus alpha n minus m. So basically what are we trying to do? We are trying to find out that we know that there are these radial lines, and the question is, where are these radial lines originating from? Where, as k tends to infinity, we know this root locus will be asymptotic to these lines, and then we want to find out where these radial lines meet. And we can find out that these radial lines meet at some alpha, which is summation of pi minus summation of zi divided by n minus m. Okay, so m of them go to the zeros, n minus m go to infinity, and these radial lines which go to infinity are at starting from this quantity alpha. So alpha is the center of the root locus. So think about it. It's a little bit complicated, but this is what is known and how we can find out where is the center of the root locus. Then we can find all the angles in which these radial lines start from the center of the root locus. And we know that n minus m branches of the root locus go to infinity, and they are asymptotic to these lines. So the last thing which we want to look at is what is called as departure angles from poles and arrival angle at zeros. So we know the root locus will start from poles at k equals 0, and some of them, m of them, will go and end up in zeros. So we want to know at what angles they depart the poles and at what angles they arrive at the zeros. There are some of them which go to infinity along these asymptotic lines. Okay. So let us pick a test point S0 very near to a pole, and we compute this angle at the test point. So since S0 is close to a pole, other poles do not affect this phase angle. So we choose S0 such that the angle at S0 is 180 degrees plus k into 360. Okay, so the line from the pole to S0 gives the angle of departure. So, and the similar approach can be used for obtaining the angle of arrival at a zero. So example, so g of s is s into s plus 4 whole square plus 16. So we have two imaginary poles, complex conjugate 4 plus minus 4j, and how do I find at what angle this root locus will depart? So we draw a line from the origin to this. So this is at 45 degrees because this is minus 4 and this is plus 4. So the root locus will depart from this pole at 45 degrees, and this one will be in that other direction, minus 45 degrees. We can also find out where the root locus crosses this imaginary line. Okay, so and that is the next thing which we will look for. So the root locus will start from here and then it will go off to infinity because there are no zeros. Okay, so there is one pole which is s equals 0, and this goes to infinity in this direction, and these two poles, the root locus will start at 45 degrees and go off to infinity in this direction. So we can find out where it intersects the imaginary line, and it turns out that we can find out where it intersects the imaginary line, and that is k equals 256, and it intersects this imaginary line at 5.66. So we can substitute k of 256 and then solve this closed loop 1 plus kg equal to 0, and then we will find that it intersects the imaginary line when it is 5.66, j I of 5.66. So we wanted to find out, without actually solving for the roots, when it crosses the imaginary axis, and this was developed by Routh in 1874. It is called Routh's stability criteria. Its similar result was also obtained by Hurwitz in 1895. So sometimes it is also called Routh-Hurwitz criteria. So how does it go? Let's consider a polynomial alpha s, which is given by s to the power n, a1 s to the power n minus 1 all the way till an. So it's an nth degree polynomial. So can we say anything about the stability of a system without solving for the roots of the polynomial? We can of course solve for the roots of the polynomial, and if the roots of the polynomial are in the left half plane, they are stable. If they are in the right half plane, they are unstable. So without solving the roots of this nth degree polynomial, can we say anything about the stability of this closed loop system whose denominator polynomial is given by this nth degree polynomial? And a necessary condition for stability is all roots of alpha s must have negative real parts, which we know. And one of the conditions that all the roots of this have negative real parts is that all AIs must be positive. And if any AIs are missing or 0, so for example A2 is 0, then some roots will have positive real parts, and hence it is unstable. So these are some simple necessary conditions. And how do I find out? We construct what is called as a triangular array, and this is shown next. So the necessary and sufficient condition for stability is that all elements in the first column of this triangular array must be positive. And this is the Routh's criteria, or also sometimes called as the Routh-Hurwitz criteria. So here is the array. So we start with the polynomial, the nth degree polynomial, with s to the power n plus a1 s to the power n minus 1 all the way till an. So the first row is we take this Sn and we write down 1, a2, a4 and so on. So basically what have we done? We have taken the coefficient of s to the power n, then the coefficient of s to the power n minus 2, and all the first term, third term, fifth term and so on. The second row is the second term, fourth term, sixth term and so on. So we write the coefficient of a1, then a3, then a5 and so on. The third row is s to the power n minus 2, and we call it b1, b2, b3, and b1 is nothing but a1, a2 minus a3 into 1. Okay, so we have the determinant of 1, a2, a1, a3, 1, a2, a1, a3 with a minus sign, and then you divide by a1. So we get a1, a2 minus a3 into 1 divided by a1. So this is b1. How about b2? b2 is a1, a4 minus A5 divided by A1. So we can fill up this third row. How about the fourth row? C1 is given by B1, okay, into A3. So we go from here to here and then A1 to B2. So B1 A3 minus A2 B2 A1 divided by B1 and so on. So we can keep on computing all these rows, and how many such row will be there? There is one for s to the power n, s to the power n minus 1, all the way till s to the power 1 and s to the power 0. Okay, so we find this array and where we compute all these terms, and according to Routh, all the terms in the first column must be of the same sign. Then the system is stable. Example. So let's take the 6th degree polynomial, which is s to the power 6 plus 4 s to the power 5, 3s to the power 4, 2s cubed plus s squared plus 4s plus 4. So what is the first row in the Routh array? We say this is S6. This is 1, 3, 1 and 4. Second row 4, 2, 4 and 0. There is no other term. Then the third row, it is 4 into 3, which is 12 minus 2 divided by 4. So which is 5 by 2. Then it is 4 into 1 minus 1 into 4. So this will be 0 and so on. This row, which corresponds to s cube, it is 5 by 2 into 2 minus 4 into 0 divided by 5 by 2. So this will be 2. Then 5 by 2 into 4 into minus 4 into 4 again divided by 5 by 2, and we will get some other term. The fourth row is 2 into 0 and this into this, and you will get 3. And the s to the power 1 row is 3 into minus 12 by 5 into 2 into 4, which is 8. So 3 into minus 12 by 5 minus 8 divided by 3. This is minus 76 by 5. So the first column, this is positive, this is positive, this is positive, this is positive, 3 is positive, but then you have a change in sign. This is minus 76.5, and again the last row will get 4. So due to this negative sign, there are two sign changes. That is what Routh said. You go from 3, which is positive, to minus 76.5, which is negative, and again positive. So if there are two sign changes, there are two roots in the right half plane for this polynomial. Okay, so we haven't solved this polynomial. We have constructed this array, and then we have seen, or we can show, that there are two roots in the right half plane. You can verify this using MATLAB. MATLAB has many tools which will give you the roots of any polynomial that you give me, and you can check. But there is a proof for this Routh array, okay, and you can search in literature. So let's use this Routh array to find the value of k where the root locus cross the imaginary axis, because once it crosses the imaginary axis and goes to the right half plane, the system is unstable. So it is important to know the value of k for which the system will become unstable. So we will take this example of 1 plus k into 1 divided by s into s plus 4 whole square plus 16 equal to 0, which is s cubed plus 8s square plus 32s plus k equal to 0. So we can form this Routh array. S cubed is 1 and 32, so this is 1 and 32. S square is 8 and k. So s to the power 1 is 8 into 32 minus k divided by 8, and then this into k into 8 into 0 divided by this, so that will give me k. So what do we have? First column is 1, 8, and then this is 256 minus k divided by 8, and this is k. So if there is no change in sign, the system is stable. So when will there be no change in sign? First k must be greater than 0, and then 8 into 32 minus k should be also greater than 0, so which basically means k should be less than 256. So at k equals 256, the root locus crosses the imaginary axis. If k is greater than 256, then this term will become negative and there will be roots in the right half plane for this polynomial, and the system will become unstable. If k less than 256, the system is stable. So the last thing in sketching a root locus is something called multiple roots on the real axis and breakaway or break-in points on the real axis. So if you have a second order system with poles at s equals 0 and s equals minus f by j, so this is the well-known example now of a link being rotated by a DC motor. So we have one pole at origin and one pole at f minus j. So when kp equal to 0 at poles, okay, so as kp increases along the real axis, the maximum kp will be at the place where the two root locus meet, and that is at minus f divided by 2j. So if you go back and see the roots, the term under the square root will become 0, okay, when s is minus f by 2j, and then kp will be 0 again at s equals 0. So at the s equals 0 pole, kp is 0, s equals minus f by j, kp is equal to 0. So as if you start from the left, as kp increases, the pole is going towards minus f by 2j, and then on the real axis, if you think in that way, as you again kp will become 0 at s equals to 0. Okay, so this is what is shown here. So at this place kp is 0, at this place kp is 0, so then somewhere in between there it must be maximum. Okay, and it's maximum at this point where the two root locus meet. So, and this is the place where you have multiple roots. The roots of the denominator polynomial are equal. So in general, from 1 plus kg equal to 0, for multiple roots, k must be at a maximum. So k equals 0 here, k equals 0 here, but then it increases and then again it decreases to 0. So k is maximum here on the real axis. K of course is increasing when you go towards the imaginary, when once you go, k becomes larger and larger, the poles will become imaginary, but we are only interested on the real axis when it meets and when it breaks away. So in order to find the breakaway point on the real axis, let's call that as 0, it must satisfy this equation, which is the derivative of minus 1 by gs should be equal to 0. Why? Because k is equal to minus 1 by gs and we want to write dk by ds is equal to 0. So k is maximum. So then d by ds of minus 1 by gs must be equal to 0. So example, let's look at this g of s is 6 divided by s plus 1 into s plus 2 into s plus 3. So we have 3 poles, 3 open loop poles, and all these 3 poles, one is at s equals 0, s equals 1, minus 1, s equals minus 2, and s equals minus 3. So we can plot this root locus using MATLAB. This is what MATLAB has plotted. So one branch will go to infinity along this direction, then one branch will start at minus 1, one branch will start at minus 2, and then they will meet, and then they go off to infinity along this blue line. So the question is, how do I find where this breakaway thing happens? Okay, and that can be obtained by taking the derivative of -1 over gs and set it equal to 0 and solve for s from this equation. So in this case, it happens that for this example, s equals -1.42, and the value of k at that place is 0.06. We can also find out the value of k where this root locus breaks away. So as I had mentioned right in the beginning of this lecture, that we can always draw a root locus using MATLAB. So I am including a very short demo done by the TA for this course on how to draw a root locus using MATLAB. And in the next few minutes, he will show you how to use MATLAB to draw the root locus for a g of s given by 6 divided by s plus 1 into s plus 2 into s plus 3. There is a link to GitHub for the code and the steps. So even if you do not see exactly all the steps in the next video, you can go to this link and you can see in great detail or magnified detail what are the steps required to plot the root locus for this transfer function, for this open loop transfer function.
In this video, we will see how to plot the root locus of a system in MATLAB. So in this example, we will consider a transfer function given as g of s is equals to 6 divided by s plus 1 times s plus 2 times s plus 3. So first we will define the housekeeping functions so that we clear the screen, we clear the figure, and we clear the workspace. Here we will be using the zero pole gain method to define the transfer function. So the poles of the system are at -1, -2 and -3. There are no zeros, so that's why it is kept blank, and the gain of the system is 6. So this is how we define the transfer function. So we define it as zpk, then the zeros, then the poles, then the gains. And R locus in bracket G, so G is the system here, will draw the root locus of the system. So now if we hit run, you can see this is the root locus of the system, and you can see I have deliberately kept the output of the G here visible, so that you can see that this is the transfer function we are working with. So it is 6 divided by s plus 1 times s plus 2 plus s plus 3. So here we can see the poles are at -1, -2 and -3. They are all real in nature. You can also turn on the grid here, so I'll remove this comment and then run the plot again, the file again. So here you can see now the grid is on. Here the circles are the different values of the gains, and the straight lines originating from 0, 0 are the lines corresponding to particular particular damping value. So as you can see, this is the constant damping line of 0.22. Here this line corresponds to the damping value of 0.42 and so on. Now if you want to get a particular value of a particular point on this root locus, so we will use this data tips function. So you just click it, and now you can click any point you want of your choice. So after clicking, you can see, okay, the gain at this particular point is 6.97. The value of the S value is this value. So this is complex in nature. As you can see, this is in complex plane. This is the damping value, this is the overshoot value, and this is the frequency. Now similarly, if we want to see different values, so you can just directly drag this as cursor and you can get the different values. So if we come now to the real plane, so you can see this point is now on the real axis, so you can see the pole is also given as a real value, there is no imaginary value, and you will see this is the constant damping as 1 line, so that's why damping is 1. You can select multiple points and get multiple values of the system parameters at that particular point. So this was about how to plot and how to see different values, the different values at different points of a root locus.
Finally, we go back and see a property of the root locus or a property of the transfer function which we had deferred earlier. I had said several times that the order of the polynomial of the numerator, which is m, and the order of the polynomial which is the denominator, which is n, and m must be less than or equal to n. So let us discuss why m must be less than or equal to n. So the open loop transfer function g of s is given by y of s divided by u of s, and as I have said earlier, it is k1 into s plus z1 into s plus z2 into all the way till s plus zm, and s plus p1 into s plus p2 all the way till s plus pn. And as I have mentioned several times, and again, m must be less than or equal to n. Question is why? Why should m be less than or equal to n? So let us consider a transfer function y of s divided by r of s is just s. Okay, so the numerator is order 1, it is s, whereas the denominator there is no polynomial. So this is basically violating m less than or equal to n. Why? Because m is here 1 and n is 0. So now let's see, if you have a transfer function of this form, y of s divided by r of s is s. In time domain, I can write y of t is dr by dt. Why? Because y of s is s into r of s, and if I take the inverse Laplace transform, s into r of s is nothing but dr by dt. Now dr by dt from basic definition is the derivative of r with respect to time, which is nothing but limit delta t tends to 0, r of t plus delta t minus r of t divided by delta t. So this is very basic definition of a derivative of a function. At t equal to 0, okay, what happens? That we need information about the future to obtain the derivative dr by dt. Why? Because this is t plus delta t. So delta t is small, nevertheless it is something which is happening in the future. It's a value of r in future at t equals 0. So the derivative at t equals 0 depends on the value at t plus delta t, and this is not allowed. So basically the system is not causal. What is causal? In any causal system, the current state of the system depends only on the past values. It cannot depend on a future event or a future value. So if you have a transfer function which is y of s divided by r of s is s, then the system is not causal. We can also look at it in the terms of the root locus. So we know from root locus that the branches start at n poles and end at m zeros, okay, or at infinity. If m is greater than n, so the number of zeros is more than the number of poles, okay, then what would happen to the branch ending at m minus n zeros? So suppose you have 3 poles and 2 zeros. So the two poles will end at the two zeros. So there is still one extra zero. So which branch will end at that zero? Okay, so there is no other branch which will end at the third zero. So hence that is not possible. So this is another reason why m cannot be more than n. So m must be less than or equal to n. So in summary, if m is greater than n, the system is not causal or it is not a physical system. So this is a very important concept in root locus, or in fact for any dynamical system. The numerator polynomial must be of lesser order than the denominator polynomial. So in summary, the root locus is the geometric approach for single input, single output systems. The root locus is based on Laplace transform and is an S-domain tool for control system analysis and design. The root locus is used to find the roots of the closed loop transfer function as a gain increases from 0 to infinity. It can be used to find the values of gains for which a system becomes unstable. I showed you some rules for plotting of root locus, that it starts from poles and ends in zeros, and these are the asymptotes, and this is the breakaway angle and arrival angle and so on. It gives insight to the root locus, but most of the time we use modern computer tools to find the root locus of any SISO system, single input, single output system, very, very easily. So very few people would use all the rules to sketch the root locus, because modern computer tools easily give the root locus for any single input, single output system. And I have shown you a small video of how we can use MATLAB to plot the root locus of an example system.